Welcome, everybody. It's my pleasure to introduce Érika Roldán from TUM and EPFL, and today she will be speaking on evolution of the homology and related geometric properties of the Eden growth model.
Hello, everyone, and thank you very much, Henry and Sarah, for the invitation. I just want to mention before starting, everyone can stop me at any time, and I'm gonna be making some pauses. That is gonna be clear that I'm making a pause for questions. And yes, please feel free to interrupt me at any time. Okay, so I want to thank the European Union's Horizon 2020 for the fellowship that is supporting my research, and I want to mention that this is joint work with Ben Hart. He is right now at OSU. Okay, so this is how you are gonna know that I'm making a pause. So right now, I'm gonna tell you what is the agenda for the talk of today. So I want to start immediately by introducing the model, and then after that, I'm gonna address. Sorry, that's number 2. I'm gonna address some combinatorial and topological properties of the objects that we're going to be working with, and then we're going to jump to the topological and geometric data analysis of these objects. So yeah, wanted to let you know that this is how you're going to know I'm making a stop for questions. Good, so let's start by introducing the model. So this is the Eden cell growth model, and this model was first simulated in 1953, 1954, and it's a very geometric, discrete, appealing model. So you start with one square, and then you can think that you are in the infinite square tessellation of the plane. And what you want to do is you want to select one of these 4 tiles that are neighboring this cell, and we're going to select them uniformly random, meaning, okay, there are 4 tiles in the perimeter, then I want to select one of those tiles with perimeter 1/4. So each one of those has the same probability of being selected. So let's do that. Let's select one, and let's say that was the lucky one. Now I want to make this example with 2. So now there are 6 squares that are bounding the new shape that has 2 squares. So now each one of the 6 that are bounding this structure are going to be, it could be selected, and it's going to be selected with the same probability 1/6. So we keep doing this. Each time we have to measure how many are in the perimeter. So yeah, I'm gonna start speeding time. So here for us, time is the number of cells that we have. So in that sense, we have a stochastic process, and stochastic processes are usually or sometimes defined on spaces that take real numbers or other kind of complex numbers. But now the spaces that we're working with are geometric. So each time that we run from time t to time t+1, we're getting a new structure, and that depends on the previous one that we had. So let me show you what can happen. So far there is no indication of topology happening here, right? But we just keep going to see if something interesting happened. And then, of course, as you can be already imagining, what can happen is that you can create holes, right? And so actually this, being able to find one of these examples was not easy. To actually do one randomly and to have that the first creation of a hole had actually 2 holes being created instead of 1. Okay, so I want you to keep this intuitive definition of the model that is actually enough to follow the talk. And then just a historical remark before going on. Alan Turing was the first one to study this kind of geometric growth models, and he did it with one-dimensional cells in 1952. And I don't have historical records to back up what I'm going to say, but I think that it is possible that Eden got inspired as well from this work from Turing. Okay, so but then let's time go bigger and bigger. And I'm not going to do it tile by tile because I don't want to spend the whole talk on that. So let me just make a big jump on time. So now I would like you to look at the picture and start making some intuitive, interesting questions that you can think of. So let me pause some of the questions that you are, of course, thinking about is, okay, it seems that the holes are near we could consider the outer perimeter. And so here I'm going to take a chance to define the outer perimeter. So the outer perimeter are those square tiles that could be added at the next time and that are in the infinite component of the plane. So all of these are in the outer perimeter. Okay. So the inner perimeter is going to be all those tiles that share boundary with the structure and then that are part of holes. And here it's very clear what is a hole. A hole in this case is the number or the components, the finite components of the complement of the structure. Okay, so one of the things that you could ask, of course, is, okay, how many holes I'm expecting to see at each time? What is the area of the holes? What area am I expecting to see? And then one of the most important questions that we will be able to answer with topological and geometric data analysis, in particular with a tool called persistent homology, is, well, how long are these holes lasting? Okay, so before going to analyze the combinatorial objects that we are using, let me show you a little bit what it looks like when we leave time go higher and higher. So yeah, this is kind of the structure that we're getting. So you can start making just conjectures out of it. I'm gonna go back to all those conjectures and which fields of mathematics have already studied this structure. Okay, so let me first of all address these objects that these variables are taking. So this is a stochastic process, and at each time what we're choosing is a polyomino, and we're choosing a polyomino with t tiles, where t is the time. So here I choose to show very famous polyominoes, a set of very famous polyominoes. So these are polyominoes with 4 tiles, and so polyominoes have 2 main properties, or polycubes, or higher dimensional analogs of these structures. So the main one is that it has a connected interior, and you can also see it as if you draw a graph that has vertices in the center of the squares, and you connect the edges whenever they share a one-dimensional face, in this case, then you have a connected graph. So you can define it in these 2 ways. Either this graph that we build like this is connected, or the object has connected interior. So in the topological way, in a topological setting, we have the 0 cells that are the vertices, so they are present, and then the edges are there. So we have all of these, meaning we have pure structures. These are pure 2-dimensional, so we cannot have vertices that are not part of a two-dimensional space, and we cannot have edges. So this will not be allowed for us. So that is not a polyomino. And of course, we cannot have this structure if we are choosing from the infinite tessellation with two-dimensional squares. But without going into these technicalities, you can think of this as, okay, we take squares and we glue them together by the edges, and we want to study these objects when they are part of the infinite tessellation of the plane, so they're embedded. Okay, so let me show you one polyomino with holes. So the two smallest polyominoes with holes. So of course, with 8 tiles here, you can create a hole, but also with 7 tiles, because remember that we have the vertices and the edges. So if you were a two-dimensional creature trapped here, you will not be able to escape. So yeah, with 7 tiles you can have a hole, and with 8 tiles you as well. And
question: you can't take away another corner and get away with 6, because then it wouldn't be a polyomino. Then it wouldn't be.
Yes. So that introduced my next slide. That is one of the slides that I'm going to show. Not the next one. The next after that one. But yes, with 6 you cannot. Which is already an interesting question, right? That I'm going to address later, like the number of tiles that you need to create H holes. Okay, so the combinatorial mathematical world have been studying these objects a lot. And one of the things, Eden as well in that paper that he was sampling big Eden growth models, he also was interested in counting them. And he was the first one to find some bounds for the number of polyominoes. So let an be the number of polyominoes with n tiles. So what he showed is that for sufficiently large n, I think n equals 20, this already is correct. An is between 3.14 to the power of n. No, this is not related to pi. And then 27/4 to the power of n. And then later on, Klerner proved that, well, this actually, if we take the square, the n root of an, it converges to a constant. And now one of the open problems in the field is finding the exact constant. There are some conjectures about how an looks like. So it is believed that it looks like a constant, lambda to the n, of course, and n to the power, some power, and that power is believed to be -1. And this is the best conjecture with computational experiments that are there. So the conclusion that I want you to make after talking about the combinatorial question of enumeration of polyominoes is that it is hard. And one of the things that attract me the most when I was starting looking at topological problems with these subjects is that for n bigger than 56, no one knows how many there are. So computationally, it's as well very difficult to go higher than 56 to know the number of polyominoes. Now, okay, we don't know how many are.
What's special about 56? Was that just the greatest they could work up to, or is there something
yes,
special about that number?
it's the I mean, they cut it just the computations that they were making. Yeah.
Okay.
I mean, I guess you could keep going, but it will be that so far they got so far there, but the computations you can keep going. But now that you address that question, so in the kind of computations that they do, they can actually look at the structures. So in 2015, Tomas, Rivera, Silva counted polyominoes up to 28 tiles, and but it's different than what they do in the other, what I mentioned before. They know how many there are for n equals or less than 56, but they were not able to actually have them in the memory to analyze some of their properties. So Tomas Silva was basically interested in the symmetries. So if I give you a polyomino, how symmetric is this polyomino? And then one of the great things that came out of it, and he was not actually interested in particular in this question, but he kept track of it when he was observing each one of the polyominoes, is, okay, I want to know the number of polyominoes that have 1 hole, 2 holes, 3 holes, 4 holes, etc., with certain number of tiles. So, for example, here we can see what Henry just mentioned, right? If you have 6 or less squares or tiles, you have no holes. Now, there is 1 hole that appears when you have 7 tiles, and then you have to wait a little bit more, up to 11 tiles, to be able to create 2 holes, and so on. So this was already very, very, very interesting, and of course, in a combinatorial sense, this is an extreme topological problem in terms of, okay, what is the minimum number of tiles that you need to create H holes, or what is the maximum number of holes that you could create with N tiles? And this is not the topic of today, but I think it's good to start showing some extremal structures that are very different from random structures. So let me show you some of these. And what you're going to be looking at is part of a research, the research project with Matthew Hale. I did it on my PhD thesis as well, and it is on. So if you have n tiles, let Fn be the maximum number of holes that you could create with n tiles. So in 2018, we proved that it grows as 1/2. And then very nice structures came out of this. So for example, we were able to calculate exact values and not only to have the asymptotics. So these are polyominoes that are part of a sequence, and this sequence reaches the maximum number of holes. So I'm not going to go into details, but some of you might already be inspired on finding how these were created. So yes, S2 is created out of S1 and as well by some elementary movements. Okay, so let me show you one figure just to have a comparison with what we can see when we sample a random polyomino with some probability distribution, in particular with the Eden model distribution that we're imposing with that model. So this is a polyomino maximizing the number of holes. And other interesting things that you can find here, a periodic tessellation, space filling curves, etc. So this is a whole other topic. And of course, everything that I'm going to be talking about, you can think of it in other tessellations. So for example, with Greg Mallin, we address the same question, but with triangles. So we already solved what is the maximum number of holes that you can create with n triangles, and if you want to have h holes, what is the minimum number of triangles that you need for that? Okay, so that was all I'm gonna say in terms of combinatorial and extreme topological combinatorics questions. I'm gonna go back to the random world, so I would like to ask if there's any questions before going on.
I just had a history question. So Turing is Alan Turing of computability?
Yes. Yes.
Huh.
Yeah,
did he work a lot on these things, or was it sort of just for a couple years, a couple projects?
As far as I researched, there was only one paper on that. But of course, I'm not sure. I was not really looking into that.
Thanks.
Yeah. Mm-hmm. Okay. So let's keep going. So I'm gonna go back to the Eden model, and one of the things that I would like to do is to address some interdisciplinary aspects of the Eden model. So the Eden model was already has a lot of attention in the first passage percolation community, in the probabilistic community. So I'm going to introduce the first passage percolation model. I want to say it is not the model, it is not the Eden model as I introduce it. It's a different model, and I'm going to spend around 3 minutes on that. If someone is not into it, is okay. I'm going to go back to the Eden model, and you don't need this. It's just for whoever is interested in this kind of questions. Okay, so now what we have is the infinite grid, the d-dimensional grid, integer grid, and we're going to put in the edges identical distributed and independent variables. And you can think of those as the time from passing. So for example, if I have here one of the vertices x, and we have here another vertex y, and we have, for example, here 0.5, then this means it takes me 0.5 seconds to traverse this edge. Okay, so, and then whenever you choose a path, any path, once we have run this on the infinite grid, then you have in each edge number, right? The value that the variables gave you. And then if you choose a path, any path, so you choose x, and then you choose a path to move to y, and then you want to know how much time costs to go from x to y in this time, well, you add up each one of the times that are in each one of the edges of the path. Okay, and so this, of course, is giving us a random discrete metric space, because each time that we run again the experiment, we get a different metric space. And how do we put the metric? Well, we're going to take the infimum over all the paths that connect x and y. So you have one vertex here, and then another vertex there, and then you ask, okay, what is the distance between x and y now that I have run the experiment? Well, you're gonna go and look to all the paths, and perhaps there is a path, this path, that got the infimum of the time that you will get to go from x to y. And yeah, it is, and then this is gonna change with each one, every time that you run the experiment, it's gonna change, of course. So, and these are gonna be the geodesics, the infimum that you get. Okay, so now, whenever you choose a radius, now I wanna emphasize that I'm using r instead of t of time, and this is important. Whenever you choose a radius, we're gonna define the ball of radius r to be equal to all the vertices that are at less or equal distance equals to, or less or equal distance r from the origin. So one of the important things here is that we are not controlling the number of vertices that are at radius r, and this is different with the Eden model. But of course, there is a relationship between these two models, and let's look at that theorem. But let me mention before looking at the theorem. Yep.
By passage time, do you mean a first passage time to go from what to what?
So the first passage percolation model is actually telling you what is the first time that you can get, for example, from x to y, or you want to know all the points that you could get to at time, or okay, at radius r. Okay. The point is that I don't want to use time there. Yeah. Okay, so let me tell you some traditional questions that people look at in this area. So the typical asymptotic distance, or the expected asymptotic distance, the geometry of the ball. I'm going to go back there with some pictures, and the main theorem of the field, the geometry of the geodesics, and what happens if we change the distribution on the edges. How does the metric space change with respect to that? And the theorem Richardson's proved in 1973, that is actually the main theorem that connects this first passage percolation and model and the Eden model is that if you take the variables in the edges to be exponential with mean 1, it has to be that particular distribution. And then you define these variables. So these variables, sigma k, is going to be the infimum of the radius at which you have k tiles in the ball of radius r. So now we are forcing how many tiles we want. Then, if we represent by gt the Eden model at time t, this Eden model at time t and the ball of this model that we have defined combined with these variables that you just defined, sigma of t, are going to have the same distributions. So it is important to mention here that actually the radius is behaving as t to the 1 over d. Okay. Okay, so that was it with respect to the area of the first pass percolation. But one of the most important problems in first pass percolation is the boundary and the limiting shape, and it's an open problem. So if I show you this here, I have erased all the tiles that are not sharing any boundary with perimeter, even whole perimeter or the outer perimeter. So if you look at it, and if I make a quiz and we vote, so I don't know how many of you will say, oh, this looks like it is converging to the circle. Well, we know a little bit about that. So in 1986, Keston proved that 4 dimensions were equal to 500. The limiting shape of the Eden growth model is not an Euclidean ball. So those are okay. So it's a little bit more beyond my imagination, 500. But then in 2011, Kernan, Enriquez, and Guerin proved that if the dimension is fewer or equal than 35, then the limiting shape is not an Euclidean ball. And up to my knowledge, this is the latest result on this. And of course, for d equals 2, it is an open problem. We don't know if the limiting shape is a ball or not. So let me formalize what we mean by the limiting shape. So the limiting shape is going to be a set B that is convex, that is non-empty, and such that you can place B inside of the structure and outside of the structure in such a way that the shape is totally contained in it, and that you have the one that you place in the interior completely filled. So this we mean, but if there exists a limiting shape. Okay, so if someone is interested in this kind of problems, I really suggest to go into it. There's a very exciting area. Okay, so, but we're here for a new way of trying to understand these stochastic topological problems. And then we're gonna look at the microstructure of the boundary and to look at the holes. And we want to know what is the shape of the holes, the area of the holes, and we want to know how the holes are behaving in terms of when they are being born and when they are dead. Okay, so before going on, are there any questions? No? Henry, do you hear me?
Yeah, definitely.
Okay.
Do you want to go on the public YouTube record with a guess for the d equals 2 case, whether it's a circle or not?
So you stopped listening to me or something? Or I don't know.
No, I said, do you want to go on the public record with a guess for the d equals 2 case, whether the limiting shape is a circle or not?
Okay. Yeah, I mean, it wouldn't harm my CV to do that, right? Yeah. Yeah. Okay. So let's keep going if there are no any questions.
Sounds good.
Okay. Great. Yeah. So, well, as I mentioned at the beginning, we're interested in the evolution of the whole. So I'm not gonna introduce Betty numbers to this audience. I think there are wonderful records of a lot of talks given in this seminar that people can look at, and one of those videos were given recently by Omar Burboski, and actually the structures at least are some way similar, at least the geometric objects. So I encourage people to look at other videos of the seminar to look at the specific definitions. Okay, so for us, or you can keep with the two-dimensional intuition, that is, holes are the connected components, defined connected components of the complement. Okay, so let's look at the evolution of Betty d minus 1 of the Eden model at time t. So let me show you one experiment run up to 100,000 tiles. So this is Betty 1. So yeah, could you guess? Does someone in the audience want to guess how it is behaving? Yeah, I would like to know if someone wants to say, I know. I think I know how it is behaving. No? Okay.
Is it like a square root?
Yeah, it is. So let's.
I've seen your talks before, so
yeah. So let's after doing a lot of experiments, it looks like it is behaving at 1.22 square root of n. Yeah, and some statistical tests. Okay, so why is it behaving as a square root of n? Well, the perimeter is behaving also as a constant square root of n, and all the holes are pushed to the perimeter. So that is kind of the intuition behind it. Okay, so now one of the questions that one could ask is about the jumps of the number of holes. So we could ask, okay, how many holes can I create from one type to the next one? The maximum number of holes that I can create. And so you can create up to 2 holes. So if Betty 1 is the first Betty number of the two-dimensional Eden growth model, then for any time, the difference between Betty 1t minus Betty 1t minus 1, so we're in 2 dimensions, is either you cover 1 hole, of course, either you do nothing, either you create 1 hole, or the upper boundary is to create 2 holes. So yes, you cannot create 3 holes, and all of the values are attained with positive probability for all times. Actually, here is time is bigger than 9. This is not correct. Should be 9. Okay, so this theorem characterizes, at least in 2 dimensions, how Betty 1 is the change of Betty 1 that we can observe from one time to the next time, which is the jumps that you see in this plot. Okay, so let's do more experiments. So now let's go up to 200,000, but we have done this to up to 1 million. What you observe here now is Betty 1 in the red one. You have the function 1.2 square root of n in blue, and then you have the perimeter, and in this log plot. And it is really clear that Betty 1 is converging to the perimeter, sorry, to the function of n, and that all of them are behaving as square root of n. Okay. So up to now, there are only experiments. So based on these experiments, in my PhD thesis, I conjectured that the expected number of holes, Betty 1, time t, is bounded below by a constant square root of t, and bounded above by a constant square root of t. And actually, the constants are behaving very stable between 1 and 1.5, and actually you just saw that is actually lower, but I wanted to go safe in this slide, in this conjecture. Okay, so this I was not expecting to solve this conjecture soon, but then we just prove it in collaboration with Ben Hart. So we are conditioning on a long-standing conjecture. So let's look at the whole statement and why it makes sense to conjecture on that. So let PDT is going to be the perimeter, the side perimeter of the d-dimensional process, the Eden model at time t. And now suppose that there are two constants and some alpha between 0 and 1, such that the perimeter stays between these two functions with high probability as the time goes to infinity. Then there exist constants so that Betty d minus 1, so we are in the top dimensional homology, or the top dimensional, the top dimensional homology, top dimensional holes that you can create, or cavities sometimes in an intuitive way, is going to be also bounded between a constant time to the alpha and below, and a constant time to the alpha below, with high probability as the time goes to infinity. Okay, so I just want to mention that the proof is along the lines of making some coupling with a multinomial distribution. Okay, so and if someone wants to, I would like to remind you that when you have a sequence of events, in this case it's a sequence of events that is indexed by the time, then that sequence of events happens with high probability if the limit when it goes to infinity of the probability of the events equals 1. Okay, so now let's look at a three-dimensional case. So now we're jumping to three-dimensional, and of course this gets more interesting in terms of the topological things that can happen. So now we can have Betty 1, Betty 2, and we can as well measure the perimeter. Now the perimeter are going to be those side cells that share a square or a 2D phase. Okay. So you can see here that there is a change at some very short time in terms of the behavior of Betty 2 and Betty 1, and it was a little bit surprising, but the intuition is there why Betty 2, or the voids that we're creating, are more than Betty 1, and basically is more difficult to maintain or to create Betty 1 because you need more cells, that you need them not to be present and to be present in the structure to actually create or destroy Betty, to create Betty 1. Okay, so so what about the jumps that we are observing here? Well, we also have a theorem characterizing these jumps. So Betty d minus 1t is a d minus 1 dimensional Betty number, and then for any t bigger than, and again we need here 3 to the power of d minus of 3 to the power of d, we have that Betty d minus 1t minus Betty d minus 1t minus 1 is bounded above by 2 times d minus 2 and bounded below by minus 1. And it's going to take all possible values with positive probability at each time. So it could take any value. Okay, so this characterizes the jumps of how the Betty number can change. Okay, so let me make a stop here and ask if there are any questions.
None for me.
So, no? Okay. So let's keep going. So before going to the part of the persistent homology, I want to show here a structure that allows us to see the Betty 1 hole here. So in 3 dimensions, just the intuition in 3 dimensions, whenever we have a window built, window where the air can flow, then we have a 1-dimensional hole. And here, for example, we have a 3x3 cube, and even if you see 6 windows, well, when one plugs in things into the definition, we have 5 1-dimensional holes here. So physically is very different, the interaction that Betty1 holes and Betty2 holes have with the medium. So if we had here one Betty2 hole, then we couldn't see it, right? Because we will need, for example, the 26 cubes of this 3x3x3 cube, and the middle one not there. So we couldn't see the Betty2 holes. Okay, so now let's look at the persistence of these holes. So now we're looking here a plot on when the hole was the birth of a hole in the x-axis, and in the y-axis what we do is we take the death time and we subtract the birth time. Okay, so, and the black line is the perimeter. So I want to mention that this is a little bit biased in terms of course, there is at some point that this decays, because these holes that were born, for example, at this time will not have enough time to die. So to be meaningful, perhaps you could look at up to this, right? But then one of the interesting observations here that we would like to prove is that pH1, or the persistence of the 1-dimensional holes, is smaller than the persistence of the 2-dimensional holes, and the intuition will be that it is easier to kill a 1-dimensional hole than to kill a 2-dimensional hole. And if we go back, what happens here is, for example, if I want to kill, this is very intuitive, but if I want to kill this 1-dimensional hole, I can place one cube here, exactly like exactly in that spot, or I could place it just here, right? Not there, but touching just with one face here, or I could place it in the middle, and actually in the middle will kill all the holes. But then there is more chance to covering a hole, and so the probability of placing a tile in a particular spot is 1 over the perimeter present at that time. So that's the intuition behind why pH1, the death minus birth, or the behavior of pH1 is different than pH2. Okay, so now let's get rid of this bias that we have here in this region by now looking at the time that the holes die instead of the time at which the holes were burned. So again, we have in the y-axis the persistence, death minus birth. The perimeter of the structure is in black, and then we have pH1 and pH2 plotted there. So now you can see more clearly that pH1 is have death minus birth in average smaller than pH2. So by the way, this is the average of 10 runs of 100,000 simulations of the Eden model. Okay, so are there any questions so far?
Is this pretty recent that you've been looking at this, Érika? Or just,
yeah, it's pretty recent. Yes.
It's very nice data.
Yeah, it's amazing, and one of the very interesting things is that it is topological and geometric data analysis. So the topology and the geometry are going hand by hand here, right? And one is explained in terms of the other, and in particular, I think topology gets explained by the by the geometry, but also aspects of the geometry are explained about how the topology is behaving. So yeah, it's very exciting. Yeah, and we can do the same for any dimension, but we lose intuition, right?
Right.
Yeah, but we are doing this for higher dimensions as well. Okay, so if there are any other questions, then let me go to the last part of the talk, and then I'm going to emphasize a little bit more the geometric aspect that we are looking at as well in this project. So it's very, very easy to state. So let's look at the area of the holes. At least in the two-dimensional case, it is very intuitive. So we want to know what is the typical area of a hole of the Eden model. And we want to know if this changed with respect to time. We want to know, now that we have the persistent perspective, if it changed, if we look at when the holes are just burned, or if we look at some time in particular. Because if we look at some time, I cannot tell you how old are the holes, right? So this hole could have been from the beginning of area 1, but could have been of area 2 perhaps, right? Could have been that this other tile was part of the hole. So if we cut at some time and we look at the area of the holes, we don't have the persistent vision of what had happened or what is going on with the area of the holes. So for instance, we could ask for the maximum hole in terms of area that was created. And then for sure, if you take snapshots, so if you look at this snapshot, for example, 7 is the maximum area that you will have, and that is right there. But if you could keep going, for example, here, I can bet you that we will not have, I mean, there are some that are have a little bit more area, but I can bet you that we will not find one with a very big area. So those are the questions that we're addressing in this project as well, and I think the paper is going to be soon in the archive. Okay, so I wanted to show one example. So here we're looking at 1 million. Time 1 million. So we let the cell growth model run for 1 million. That's the time. So we have 1 million tiles. And then I'm showing you here the histogram of all created holes. Of course, it is with respect to 1, right? So all created holes, so 0.8 of the total of created holes that were created along all the process have area 1, and then around 1.1 to have area 2, and so on. And you can see that there is a really different behavior between when you look at all created holes, the area of all created holes, and then when you look at the holes at time 1 million. So you take the snapshot at time 1 million, and then you do the same statistics. And this is what we are observing. Yeah. So. And
so is the dark orange the overlap of the blue and the light orange?
Yes, yes,
I see.
They are overlapped.
Okay,
yeah,
thanks.
Yeah. Yes. So let me finish. Let me close. I think it's time for closing. Showing you a picture of another model. This is not the Eden model, but I just want to show you that this same question applied for any other distribution and processes that we analyze in these kind of structures built with squares, polyominoes or polymers of any dimension. So this is what you're observing here, and this is another research project that I have been working since my PhD thesis. So here we have a percolation distributed polyomino, and it has been sample with Monte Carlo metropolis hasting algorithms. It's actually a very difficult, it's not as simple as the Eden model, but I wanted to show you that the holes are really different located. So even if you have two models that have the same amount of holes, the geometric distribution of the holes can be different. And I think it's important for the physical, for the applications to physics or the chemical applications to notice this difference, that even if we measure the persistent homology, or if we measure only the Betti numbers, then I think if there is coming from a physical or it has a physical interpretation, it is important to actually say something about the geometric location and distribution, or even some other geometric properties as the area of the holes. And yeah, this is a joint work with David Aristov. We're working with these other probabilistic distributions. And with that, I would like to thank you for your attention. Yeah.
Thanks so much. So for everyone in the audience, please go ahead and try to unmute yourself, and let's clap for Érika. Wonderful. Thanks for the great talk. Are there further questions?
I just had an observation. This is Ira. This is going to sound kind of crazy, but the histogram, which I very quickly looked like something from Benford's law, if you're familiar with Benford's law.
No, I'm not.
Benford's law is a very strange thing about the distributions of digits, and the histogram just struck me as looking very much like it. It's just a thought. I'm going to play with it later. I just thought I'd throw it out there for you.
Yeah, thanks. Actually, if perhaps if you send me your email here on the chat or something, I would like to know more about it. Yeah, this is the first time that I hear about it.
Okay, I shall.
Thanks.
Think I have your email. Okay,
Thank you.
Érika, I had a question. So can you say a little bit more about this model that you're doing with David Aristov? I mean, just looking at it, it's clearly not the Eden model because there's Swiss cheese holes throughout. But how is this image created?
Yes. So we are well, as I mentioned at the beginning of the talk, these are very, very difficult objects, the combinatorial objects to work with. So in the Eden model, it's very easy to simulate them because actually we don't have a target distribution there, right? The distribution is defined in terms of the process, of the stochastic process. Now here, what we have, for example, in this case, is we want to put a distribution on the set. So if you let AN be the set of all polyominoes with n tiles, right? What you want to do is you want to assign a distribution to each one of these elements that resembles a percolation model. So let me show you this, because I promise we didn't talk about it before. But then here, what I do is I step in each one of the squares of the infinite tessellation of the plane, and I throw a coin, right? A coin with probability P. We're gonna put a tile, and with probability 1 minus P, you don't put a tile. So we do this, and usually what people in percolation do is that they look at the giant component. So they look for what is P. So what is the threshold for P that if I run this experiment will give me an infinite component? So that is one very interesting question. But what if I want to analyze for a particular P all those polyominoes that have 4 square? So I go and I look at all of them, right? And then I start analyzing their properties. So of course we don't have holes with 4 squares, but we could be looking at bigger polyominoes, right? So let me give you one that is more interesting, I think. So this one, and it actually has a hole there, right? Yep. So the point is that, okay, now it's unrealistic to look at, to study these polyominoes that are constructed with this in this way, to do it like this, like, okay, run an experiment in a very, very big grid and go and look for all of them that have, for example, 50 tiles. So this isn't realistic. What we do instead is we take a polyomino A that has n tiles, so this n is coming from the number of tiles, and then we define its probability of being sampled from the set of all polyominoes with n tiles as p to the n, 1 minus p to the perimeter of A. What the perimeter of A, because we want it to be isolated for the rest of the structure, over, you just normalize to have a distribution. And so I prove in my thesis that actually for any p that you select, the expectation of PT1 grows linearly with respect to the number of tiles. So in the Eden model, will be with respect to the time. And by the way, all polyominoes have a positive probability of appearing in the Eden model. But the point is that the model favors some of them. And the ones that it favors are the ones that have the holes pushed to the boundary, right? So that's why you will never look at structures like this in the Eden model. But if we use Monte Carlo metropolis hasting algorithms to look for those constants, depending on p, the probability that we choose, then we can have statistical evidence on, okay, they're growing linearly with respect to the number of tiles, but we want to know the constants. So we're also analyzing the area. Yeah, the collaboration with David Aristov is going really. It's pointing out to really interesting questions that are gonna be an interesting comparison with respect to the Eden model. Yeah, thanks for the question.
Certainly. Any more questions for Érika? Well, if not, thank you again, Érika, for a fantastic talk today.